I just wanted to repeat that we will have on October 10th, the midterm details will be posted in syllabus shortly. Yeah, so please attend lectures. Please don't skip lectures because this is very important. I mean, we will cover a lot of important material today also. So regarding the project, I will think if I can. I mean, I know that some people ask me to extend the deadline or something like that for checkpoint. So I'll think a little bit. Probably I'll give a little bit of extension for the checkpoint. I'm not sure whether that will automatically give an extension for the final deadline. So that may still stay the same. I think it's October 13th is the final deadline. So that I think I'm not sure, right? So because because you were like still finding partners, like switch groups, and some of you also have midterms. I may extend it by a little bit, but not much. So maybe by just a little more, a couple of days or so. I will decide. I will let you know maybe today or tomorrow. So we'll have some extension, but it's not going to be a big extension. Okay. Sorry. So last time we talked about page tables, virtual memory, and how we handle page faults, how we allocate pages, and we also okay, the battery. I need to replace the battery. And we also talked about the page table, page size. Last time we talked why it's important to have power of 2 number for the page size. And more specifically, the reason for that was that if you don't use power of 2 numbers, we have to divide. But if you use power of 2 numbers, we can directly take the page offset component from the address, because we have binaries, right? So this is why it's easy to extract power of 2 numbers from the address itself. So last time we talked about virtual page number and virtual page offset, and the same thing is for physical page offset and physical page number. So let's see how let's look one more time how we can extract this from the virtual address. So let's say a virtual address is a pointer in your program. So we have virtual page offset and virtual page number from 0 to p minus 1, and p is the number of bits in the page size. So let's say we have 12-bit page size, so that 2 to the power of 12 is 4096 or 4 kilobyte. So you have 4 kilobyte pages, so it's going to go from 0 to 11, just as an example, right? And then virtual page number is going to go from 12 to n minus 1, and n to the power of n is the memory size, right? So virtual memory size. So let's say it's a 32-bit virtual address space, then it's going to be then it's going to go from 0 to 11 and then 12 to 31, right? So this virtual page offset is going to be 0 to 11, and virtual page number is going to be 12 to 31. So okay, so we have a page table, right? And we need to store the address to this page table somehow, right? So the CPU has to know about the address, so that the CPU can let the memory management unit know and so on. So we store the base address in a special register. It's called a page table base register. So now in the page table, we effectively have an array of physical page numbers and corresponding bits, right? So we have basically an array of entries, and each entry contains physical page number and some permission bits. So by the way, we also want to use these entries wisely, right? So what I mean by this? So we want to store physical page number, but we also want to pack in the same entry this bits, just like you do for malloc. You use size and you recycle lower bit to indicate whether it's allocated or free block. The same thing here. So we want to have a physical page number, which is maybe in a 32-bit processor, assuming that you use 4 kilobyte pages to the power of 12. So it's going to be 20-bit number, right? 32 minus 12 is going to be 20-bit. So 20 bits we're going to use maybe for the physical page number, and 12 bits we are going to use for permission bits or whatever other bits we have, right? Like we will say it's a read-only or not read-only page. We'll say it's a supervisor, not supervisor page, whether it's present or whatever is called valid here in this picture. That's another bit, right? So that way we can feed both the physical page number and bits in the same entry of like 32-bit, right, or 4 bytes. So you can still use normal 32-bit entries, and this way you will fit everything there. So then the array, you'll have an array of 4-byte entries effectively, right? So then your index to this array is going to point to the virtual page number. So if my virtual page number is 1, I'm going to go to index 1 and read the corresponding entry of this page table at that location. So it's effectively an array of entries. So the translation happens, again, I extract the virtual page number, I go to the corresponding index in this array, and then I will read the physical page number and permission bits. So do you have any questions so far about the virtual page number and virtual page offset? So again, we just split it directly from the address. So the moment we see the CPU sees the pointer, or like I shouldn't say CPU, memory management unit, but it's technically part of the CPU chip. Yeah, so it sees this address, it will extract the virtual page number, it will go to an array which is basically a page table, right? So and then get the corresponding page table entry, extract the physical page number. So by the way, the page table base register, does it contain a physical address or a virtual address? Because it's kind of unclear in this picture, it just points to a page table, but is it a virtual address or physical address? Physical, right? So why is that? Because we don't want to depend on any previous page table, right? So because we would need to translate that address. So we just directly communicate to the memory management unit the physical address where the page table is located, so that no further translation for the page table itself will be needed, right? So because otherwise we are dependent on some previous page table, that wouldn't make too much sense. Yeah, so especially when we switch from one process to another process. So we want to put a physical address here. So let's see how the address translation will take place. Let's look at first example when we have a page hit. So the CPU, in the CPU chip, we have CPU and memory management unit. So CPU issues the virtual address, because the CPU always deals with the virtual addresses. Whenever you have any pointers, that's a virtual address. So the memory management unit will see this virtual address and effectively say, okay, I need to retrieve the corresponding page table entry for that one. Because remember, from the virtual page address, we can extract virtual page number. then virtual page number is basically an index in the page table array. And we now know, let's say, that we need to retrieve page table entry 1. So the memory management unit will request that. Remember that memory management unit also knows where the page table is, because the base register contains the address to the page table, and it's a physical address, as we previously mentioned, right? So therefore, it knows exactly where in physical memory it needs to read this value from, right? So it's puts this address to the memory bus and retrieves the page table entry. So by the way, it doesn't have to be memory, it can also be cache, L1 cache, so it's just combined, right? So so it can try to go first to L1 cache and then go to memory. So now, once you have page table entry, once the memory management unit has it, now it takes the physical page number, combines this page offset, gets the physical address. So at that point, we can read the corresponding data, right? So we can issue the physical address to memory and retrieve data back to the CPU. So now if you look at this picture, it seems like we have some overhead, right? So it seems like previously we just need to issue a physical address and retrieve data. But now we have to do, like, we have to retrieve the page table entry and then process it, and only after this we can issue a physical address. So it seems like every memory access will become quite expensive, right? But fortunately there is a way to optimize it, and we will talk a little bit in a moment. Okay, so page fault. Let's say we have a page fault. So this is when your page is not in physical memory. So this is when it's in the disk. So the processor sends a virtual address to memory management unit. So the memory management unit knows what the page table entry is. Again, it will request the memory to retrieve that page table entry. Okay, we'll retrieve it. And then memory management unit realizes that the page is not present. How does it know? Well, the corresponding bit will say that it's not present in the page table entry. So at that point, an exception or trap will be generated, and you will go to the page fault handler in your OS kernel, right? So and at that point, we will bring a page. So we'll first have to choose the victim page, the one that we want to evict from physical memory. So that's going to be based on some page replacement algorithms, which we'll talk later in the course. But we have chosen some victim page from the physical memory. We retrieve the page that we are supposed to bring to memory, and now it's in that location. So at that point, the page fault handler can exit, and when the page fault handler exits, it will repeat the same instruction again, and now we have page hit. The second time we try it. So it's the same situation as in the previous picture. So so there are two issues here. So first issue that I mentioned, that we need to do this translation page table entries. It's like an extra step that we need to take, and this is really kind of get expensive. But if you have more or less locality, maybe you're on the same page, hopefully it's going to be the same page table entry as an example, or there is some solution to that also, to as long as addresses remain more or less local. But then there is another issue. Another issue is that if our working set size is less than main memory, then it's fine, right? We keep everything in physical memory, and then it should be fine. But the moment that we have like a sum of working set exceeding the main memory size, so that means we are forced to keep something on the disk. So the moment that happens, we will have to bring pages back and forth. I mean, no matter how good our algorithm is, page replacement algorithm is, if if we really have to access all these pages, and it's like, I mean, we have to evict one page, then bring another page, evict one page, and bring another page, that's going to be disastrous, right? Because you will effectively, your memory speed will reduce to your disk speed, right? So yeah, so at that point you will have so-called thrashing, right? So, and thrashing means you're gonna be evicting pages, bringing back and forth, right? So that's going to be taking too long time, and that's not going to work well. So again, that's not going to be an issue if you have locality, right? So if more or less you have a certain number of pages that at any point of time that you need to work with, then it's fine. But if you are jumping from one page to another page to another page, that's going to be a problem. That's not gonna, hopefully that's not gonna happen in a typical program, but you know, you can probably come up with a scenario like this. You have a question?
Yeah, I was wondering, by working set, is that just like a cache?
Well, you know, so the programs will access some pages, right? So that we can define as a working set, right? So what pages they're accessing. So, and you can have multiple programs, right? So they will have different working sets also, right? Yeah, so if it kind of exceeds your main memory size, then it becomes a problem. So now let's look how virtual memory and cache can be integrated. So we have pretty much the same thing, CPU memory management unit. So memory management unit is going to issue page table entry request to L1 cache. So that's going to be the first step. So then L1 cache itself may have a hit or miss, right? So we may have something that we previously read from memory. It may also be a miss, and then we have to bring it from memory. So that mostly hardware will handle transparently, right? So I mean, there is some way you still can kind of influence this, but mostly hardware is doing it without your intervention or without the OS intervention. So in other words, it's not fundamentally different from what we looked at, but just kind of expanding that we may have cache and memory here. So, and again, in cache, I guess important thing here is that the cache will deal with physical addresses, right? So this we will have to use physical addresses, not virtual addresses. So naturally, if you have some page table entries in cache, then hopefully you don't need to read it from memory at the very least, right? But if you look at the cache itself, you know, maybe sooner or later, this page table entry is going to get evicted. Maybe there will be some other data stored in cache. And you know, I guess for the CPU, there is no also easy way to determine whether it's page table entry or whether it's data, because it's just, you know, just a physical address. Yeah, I guess it can determine if it wants to, but you know, it's a little bit more complicated than necessary, right? So again, you can easily get this page table entry evicted from cache sooner or later, and then you again will have to pay the price to retrieve it from memory. You know, so, and even if you have a hit, that's still some delay, right? So it's still, you have to retrieve it from L1 cache. So this is still not cheap, right? So it's not entirely free. So what kind of solution we can use to that problem? Well, we can use so-called translation look aside buffer. That's a special type of cache. So it's effectively a small set associative hardware cache in memory management unit. So the memory managed unit will directly have access to it. So the goal of the TLB is to provide fast translation of virtual addresses to physical addresses. So it will, it will contain complete page table entries, the one that you store in a page table, for certain number of pages. I mean, of course, it's not going to do that for everything. It's not going to fit your entire page table, but certain page table entries it will have. And hopefully this page table entries will be something that you use mostly in your program, right? Or in your working set. So the idea here is that in TLB, we will split virtual page number into two pieces. So, recall that we have this virtual page offset, and we don't really care about it because it doesn't need to be translated, can be directly carried over to the physical page offset. So that part doesn't need to be translated. But the virtual page number is something that needs to be translated and something that has to be handled by the TLB. So this part we can split into two pieces: the TLB index, TLBI, and TLB tag. So now let's say you have page size 4096. That is 2 to the power of 12. So you have 0 to 11 virtual page offset. And then let's say your you have 16 sets in TLB. That's 2 to the power of 4. So T equals to 4, right? So we'll have from 12 to P plus T minus 1, so which is going to be 12 plus 4, 16 minus 1, okay, 15, right? So from 12 to 15, that's going to be TLB index. And then from 16 to, let's say, 31, if you have a 32-bit address space, it's going to be TLB tag. So again, you split a virtual page number into two pieces, and that's very similar to what we did in the past for the offset and VPN, right? So let's look how that's going to work. Actually, let me draw a picture here. By the way, somehow it's very cold in this room, right? I don't know. I mean, we had the lecture in downstairs, it was not that cold. Okay, I think I can control the temperature here. Oh, is it? Yeah. Can you increase maybe the temperature? It's 6. Oh, I see. Okay. Oh. Okay, let's see. Okay, so we have virtual so we have oh, sorry, I did it. Let's say it's your virtual address, which can be in your inside your pointer, right? So let's say it's a pointer / VPN, a virtual page, sorry, virtual address VA. So you have this maybe 0, 0, 1 from 0. This is a hexadecimal, let's put it in hexadecimal, right? So this is 4 bits, another 4 bits, another 4 bits, 12 bits, from 0 to 11. right? So this is your virtual page offset. So then from 12 to, let's say, if you have 16 sets of 16 TLB number of TLB sets is 16, that means t equals to 4 to the power to 416. So the TLB index is going to go, okay, here from 12 to 15, and that's just 4 bits, that's just one hexadecimal digit, right? So let's say it's going to be 5 here. And finally we have, oh sorry, this is 15 and this is 16 to 31. So that's that is going to be maybe FF 00. So this is your TLB tag. This stuff is TLB tag. This is your TLB index. And this is the virtual page offset. So now you have this TLB index. You go to the corresponding set in TLB. So in this case, it's 5. In the slides, it's 1. You know, you go to that set, and there you see this row, right? In the row, you have tag and page table entries. So what will happen here is that you go there, you compare the tag to this value, right? So if the tag matches, so if it's a valid entry, right, the tag matches, you're gonna effectively go and achieve the page table entry from TLB. So now you can see that each row contains actually multiple columns here, right? So it has like set 1 has multiple tags, right? Like 2 tags. So that means that we can potentially store multiple entries with different for the same index, but with different tags. So let's say we have 0, 0 here, 0, 0. That's another TLB tag. And then we're gonna save 0, 0, 0 tag, right? So we can keep 2 entries. Now, if you have a third entry with some different upper bits, then of course we cannot fit it. We have to evict some previous entry from TLB at that point. So if you only have 2 columns, right? So again, the more you have there, the better, but that will also make your hardware very expensive. So again, just let me write it in binary so that it's going to be a little bit more clear, right? So you have 1. What is 1? It's 0, 0, 1 in binary, right? So then you have 0, 0, 0, 0, 0, 0, 0, 0. This is your byte offset inside the page. So once we read the page, once we know the page number, right? We go to this address. We care not about the first byte. That's not the 0, right? Offset, but we care about the one that follows that, right? So this one, right? So this one that you care about, offset 1. So this is just determines byte offset within the page. So then we have 5. This is 0, 1, 0, 1, right, in binary. So that's 4 bits. 4 bits for that determines what the set number is, right? And then you have 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, right? So 32 bits. So that determines your tag, right? So when you look at this address, clearly, clearly if we have, if this stays the same, right? Just for a moment, assume that all pointers that you have are more or less the same upper bits, right? then the only thing that changes for you is the set number. Then hopefully you can use your TLB very efficiently, right? So as long as your addresses become still local, I mean, if they're within the same page, great. We only need one page table entry to translate, right? If they are beyond the page, okay, we have different sets in the TLB, so that we can cover. So as the next step, right? So now, if occasionally we have some addresses, like some addresses like this, or maybe some zero address, maybe it happens sometimes that we have slightly different addresses, like in different portion of the memory, right? So then we have different columns, right, in TLB, which we can also address. But of course, we cannot fit the entire page table there. That would be too much. I mean, at some point, we can have a TLB miss, but that's fine, as long as, because we still cover, as long as we preserve locality. And what does it mean to be local, right? So all addresses are going to be close to each other, right? So that doesn't matter what this address is, but as long as this address is we only use mostly this, we should be fine. Okay.
Is there usually like a set value that's considered like local or not local?
Well, local means something that close to each other, right? Doesn't matter where exactly in memory it is, because again, the TLD tag, we are kind of flexible in this, right? We cannot just record the tag directly. But this one, we want to make sure that, let's say I have an array, if it's 4 kilobyte, great, that can fit in one page. We only need one page table entry. Let's say you have, maybe like 16 kilobyte array. Also fine, because you have just 4 pages. That can still fit. We can fit 16 pages easily, right? Finally, let's say, even if you have more than this, right? Sometimes you occasionally go outside of this local boundary, right? You support different tags, right? You support multiple tags for each index. I don't know if it's recorded. Let's see. Okay. So again, we retrieve the index, we go to the set, then in the set, assume it's a valid entry, right? So we compare the tag, and then we retrieve the page table entry. So TLBT matches the tag. Here, we retrieve the PT. So, okay, let's look at the TLB hit. So now we have CPU chip, right? So you have in CPU chip, you have CPU, memory management unit, and TLB. So the virtual address is issued to the memory management unit. So at that point, memory management unit extracts virtual page number, and then virtual page number, effectively we just talk about TLB. That's just two components, TLB index and TLB tag, right? So TLB gonna go to TLB index, compare the tag. Okay, if it matches, then it can directly retrieve the page table entry now, right? And we can issue a physical address directly, right? So now we issue a physical address to memory, and we avoid any other costs, right? So it's like the original case when we didn't have any virtual memory, right? So pretty much the same thing, as long as we have a TLB hit. So hopefully we'll have that situation like 95% of time, or maybe 98% of time. Sometimes we'll have misses, but hopefully most of the time that's not going to happen, right? So sometimes we'll have hits. I mean, most of the time it's going to be hits. So in that case, you see that we don't actually pay any price for that, right? So we just retrieve the we just retrieve data. So we only issue a physical address to the memory. So now if you have a TLB miss, so that means either the tag is invalid, right? Or the tag is there, but a different tag for the corresponding index. So something has to be, so that means the TLB doesn't have that entry. So at that point, memory management unit will request page table entry. It will retrieve it, store it inside TLB. So now having that in TLB, next time we access it, it's going to be cheap. But this time we took this miss, right? And we paid the price for that. And then we issue a physical address. Again, if addresses are more or less local, yeah, you can have like this cold start when you have to have a lot of TLB misses initially, but then as you run your program, everything should be fine. You have pretty much all TLB entries filled up, and you just issue physical address all the time. So we already discussed why TLB misses are rare, right? So because when we looked at the locality, assuming that your program has good locality, right? Your program is unlikely to have like 2 gigabytes there, 2 gigabytes there, like maybe 2 megabytes somewhere else. And, that's not how we structure our program. So when we compile our code data, it's more or less contiguous chunk, right? So that means that should stay pretty close to the place we care about. Or when we deal with heap, you are implementing your memory allocator, right? So you know that you're not gonna allocate more memory until you try to recycle existing memory. And existing memory is kind of close, right? So it's like it still remains local, right? So you're not gonna extend the heap unless it's really necessary. So only when you run out of memory, you will extend the heap. So this is how we preserve locality for the heap as well. So what is the problem with I mean, we talked about the page tables so far with and what is the problem with the page tables that you have noticed aside from this maybe overheads? I mean, what is the problem in terms of space? How page tables? Do you think that page tables is big or not?
Yes.
I'm sorry?
It's not much space.
Not much space, right? So, but let's calculate. I mean, it's true that in practice it's not much space, but let's calculate what happens if we just assume we use a page table the way that we use it so far. So let's say we have no, let me record it also. Let's say we have a 32-bit processor. Again, 32-bit processor. I just need 32-bit virtual addresses and maybe I'm running some hello world program or something like that. So I need to map create a virtual address space for 32-bit address space. So how many entries I'm gonna have? So remember, okay, so I need to say what the page size is, right? So the page size is 4 kilobyte, let's assume that. So that is 2 to the power of 12. So how many entries I need to have?
For one size.
For 32-bit virtual address space. I need to map the entire 32-bit virtual address space.
You would need more than 32.
2 to the power 32, this is bytes, right? But I need number of page table entry keeps pages, right? So I need to divide it by 2 to the power 12, right?
So 2 to the 20.
Yes, 2 to the 20. So that's 2 to the power 32 multiplied 2 minus 12 to the power 20, right? So that's how we get it, right? So 2 to the power 20, how much is it? By the way, there's some interview question that you can get, right? People will say, okay, calculate 2 to the power 20 without a calculator.
Okay. Is that a big place?
2 to the power 20? Well, what is 2 to the power 10? To the power 10 is 1024, right? You can check it on the calculator.
2 to the power 20 is 104.
Yeah, so let's get to the 2 to the power 20 in the second step. 2 to the power 10 is 1024, right? So 2 to the power 20, that means 1024 by 1024. That's approximately 1 million, right? Yeah, so approximately 1 million, right? So this is some question that, by the way, this is some question that you can get potentially in interview.
Just get the calculator.
Yeah, but certain numbers, you can just like 2 to the power of 10, right? So that's something that probably good to know, right? So those numbers. Okay, so we have approximately 1 million entries. So now each entry in a 32-bit processor is going to be, let's say, 4 bytes. So why is that? Well, the reason is that I need to keep the physical address, physical page number inside the entry. And that's going to be also 20 bits, right? Because again, I assume that I have 32-bit address space, right? For the physical address space. I only need to deal with pages. And maybe other things are bits like present bit, read-only bit, supervisor bit, whatever, right? So other 12 bits are recycled for everything else, right? So just like you do in a malloc, you have size, right? But you can recycle lower bits for something else like free allocated status. So the same thing in the page table, they want to keep the space wisely. So you don't, if you use 4 bytes, why not to pack everything there, right? So including physical page number as well as bits that you care about, right? So that's your page table entry. So it's 4 bytes, 32 bits or 4 bytes. So that means we have to multiply this by 4, right? Because it's 1 million entries. We have basically 4 megabytes. We have to, we have to allocate 4 megabytes for 32-bit virtual address space. I mean, for a simple hello world, I have to spend like 4 megabytes, right, on a 32-bit processor. And by the way, this is something that it may look insignificant nowadays, but when the 32-bit processor were around, 4 megabytes were actually quite significant. Maybe not the end of the world, but certainly not something that you want to waste for a hello world program, right? So it is something that we don't want to do, right? But things actually even worse than this. If we look at more than 64-bit processors, So yeah, I don't know if it's gonna get recorded, but yeah, so let me go back to this. Let me go back to this slide. So now you have so let's say we use a 32-bit, so 64-bit processor. And typically in 64-bit processors, we don't actually have entire 64-bit virtual address space. I mean, most computers that we have, they only implement 48-bit virtual address space, sometimes a little bit more than, but not entirely 64-bit. Still, let's just assume that we still have 4 kilobyte page to the power of 12, 48-bit virtual address space, and 8-byte page table entry. So now it's going to be 8-byte as opposed to 4-byte because physical page number has to be larger. So what are we going to get? So 2 to the power 48 divided by 2 to the power 12 or multiplied by 2 minus 12, right? So by the page size and multiplied by 2 to the power 3, which is 8, right? 2 to the power 3 is 8. So it's the same thing that we did right now, right? So just in single step, right? So we get to the power 39 bytes. So it's like 12 gigabyte page table. I mean, my computer has 16 gigabyte. It supports 48 bit virtual address space, but I cannot even fit one single page table there, right? So yeah, that's definitely really a lot, right? So we cannot even allocate that page table.
Forget, where did the 2 to the 12 come from?
Page table size, page size, sorry, 4 kilobyte. So that's a lot. So that means we cannot really create a page table like this. We have to use some different approach. So in that approach, so the previous approach that we had is called a single level page table. But it's not really practical. So we have to use so-called multi-level page tables. So in multi-level page tables, is like a tree, right? So you have, so now you, instead of like a linear array that we had in the past, we will create some sort of tree. So let's say we have a 2-level page table, which is, by the way, the case for a 32-bit processor. I mean, not for 64-bit processor. For 64-bit, I think we have 4 levels, 5 levels nowadays. But for 32-bit processor, we used to have 2 levels page tables. So assume you have 4 kilobyte page size, right? You have to put, how many entries can you put in each page? So now the page table also occupies some pages, right? How many entries can you put in each page? So if you have 4 kilobyte page and 4-byte entry size. So 4 kilobyte page and each entry is 4 byte. So how many entries can you fit in each page? No, 4 kilobyte divided by 4. What is it going to be? Yeah, 1024, right? 1024 entries. So in each page, we can put 1024 entries.
Then why are you dividing by 4?
Divided by, well, because I have 4 kilobytes, that's in bytes, right? I want to determine how many entries I can fit in a page. And each entry occupies 4 bytes. So I have 4096 bytes.
Yeah, I thought you said 8.
Yeah, I know. That was an example, right? But I kind of came back to the original example, right? With 32-bit process. Yeah, so again, for 32-bit processor, 4-byte entries will be sufficient, right? normally, and unless you have some exotic architecture. Yeah, so then that means we have 1024 entries in each page. So what if we split? What if we put the second, like what we previously consider as a page table? What if we just call it level 2 for a moment, right? And at level 1, we will refer to each page, right? So we can keep how many? We have to keep we have to keep 1 million entries, and each page can allow us to have 1024 entries. So we have to have 1024 pages to keep all these entries, right? 1024 by 1024, right? So what if the level 1 refers to a page of the second level, right? So the second level is assumed that's the page table that we had in the past, right? That's just an array, and we just now split it in different pages. I mean they're still going to be contiguous pages, but we are splitting it like in separate pages, right? So what if we split it in separate pages, second level, and in the first level you're going to refer to the second level. So in the first level, you're also going to have 1024 entries, and they're going to refer to 1024 entries. So let's look at the picture here. So we have level 2 table, right? So that's what we talked about previously, right? That's going to go to level 2. So now in level 2, we will just now consider separate pages. Each page can hold 1024 entries. We have 1024 pages. So in level 1, we can also have 1024 entries because it's also a single page, and each entry is also 4 bytes. But now level 1 is going to refer to level 2 as opposed to the actual physical page, right? So it's going to refer to the level 2 page. So why is it even necessary? So now it seems like we have level 2 pages, level 1 pages in addition. Actually, we have just one level 1 page, right? But why do we need to do that? What's the advantage of this? Any guesses? Okay, go ahead.
If you have a capability that you want to load people, it's already will be using it a lot.
Any other ideas? No, I mean that's fine. I mean, don't worry. Any other ideas? So what if I have this hello world program, right? The hello world program maybe just needs 4 kilobyte memory. So it's more than enough to have just one page mapped, right? So effectively I only need one page table entry in level 2. One page table level 2. Yeah, I need one entry. I still gonna waste one page for the level 2 because I cannot allocate half of the page or something like this. Okay, I'm gonna waste one page there for level 2 translation. And then for level 1 translation, I also need to waste one page because it has to point to level 2. Okay, I'm gonna spend like 8 kilobytes for that hello world program for 2 pages. But now let's say I'm gonna skip all remaining pages in level 2. I'm just gonna pretend that they don't exist. I don't need them because I only map the beginning of the virtual address space. So what will happen is that level 1 table will have nulls, right? So we'll say that this page is not there. So level 2 doesn't exist. So we'll only have the level 1 will now only have the first pointer. It will point to level 2 page, and that's it. So we only have 2 pages, level 1 page and one level 2 page, and that maps our hello world program. So we now have to waste 8 kilobytes. I mean, it's still probably more than a little too much for this hello world program, but it's fine, right? 8 kilobytes is almost nothing, even like even in the past, right? We didn't care too much about kilobytes. Yeah, so we can definitely afford creating that page table for every process, right? So now it's more reasonable. So now we don't have to have 4 megabytes. We can create a much smaller page table. So what else we can do? Well, if you have some randomization, maybe you are not starting from the beginning, but you are somewhere in the middle, it's still gonna work because you're gonna skip initial level 2 pages in the beginning, and then maybe in the middle of level 1, you're gonna have a valid point to level 2, and that gonna point to level 2 page. So now we don't really have to have a contiguous range of level 2 pages. We can skip entire regions there, right? So once we have level 1. So we can really have big gaps in level 2. So let's look at this example more specifically, right? So we have virtual memory, right? Virtual page 0, virtual page up to virtual page 123, virtual page 124, so on, right? Then you can see there's a gap in virtual memory, right? There is a big gap. Then unallocated pages also after this gap. And then finally, we have one allocated virtual memory page at the end, right? So maybe for stack or something like that. So how are we going to represent? Because remember that in practice, you don't have a contiguous virtual memory. Remember that heap and stack go in different direction. I mean, for heap core data, maybe you can fit in the beginning, but stack goes to the opposite direction from the opposite side. So it's natural to have gap in between, right? So how are we going to deal with this? Well, again, for virtual memory 0 to 1023, we have to have page table entries in level 2. So that's going to be 0 to 20, 0, I can show it. Okay, 0 to 1023. So we're going to have this corresponding entries, right? So for the second range of addresses, we have the second page in level 2. So now, after this, we have a gap. We don't even need to allocate anything for this in level 2. So what will happen in level 1, we're going to point to this level 2 page. PDE 1 is going to point to the second page. Then we have a big gap. We just skip it. We don't allocate any level 2 pages. And so we're going to put null here. And then finally, we're going to reach this address. So we still need to deal with this address at the very end. So how do we get there? Okay, let's calculate it. Okay. We need to wrap up, right? In a second, okay. Yeah, so how do we calculate it? It's 9215 is 8,192. That's going to correspond to 8,008 entries, and each of them points to 1,024 4 entries in level 2, right? So we skip from 0 to 7, we skip it. So that's going to be 8,192 entries from 0 to 7 in level 1, right? Then we care about PDE 8. So that's going to be the last one. So this number is going to be 1023, right? If you calculate it, you can check it on the calculator. It's going to be 1023. Yeah, so that means it's the very last entry of level 2. Right, so it's so that means again in level 2 we're going to skip 1023 entries. We're going to put nulls there, and the very last entry is the one that's going to point to 9,000 right? So in just does it make sense? Yeah, so this is how we can skip entire regions, right, of the unallocated memory. So in the last thing I wanted to mention today, remember that let's look at the virtual address one more time. We have virtual page offset that's going to be directly transferred to the physical address. We have a virtual address can be split into different components, right? Once we have multi-level page table. So if we have two levels, so the VPN K, right, VPN2, that's going to be closer to the virtual page offset. Let's say 10 bits. We have 2 to the power 20 and 32-bit processor. 10 bits we will dedicate to level 2, and 10 another bits we will dedicate to level 1. So this is how we can determine which index in each level you have to go to.